Hello, Tensor friends. I've got another problem today here, posted on 7/27. Okay, in the last video, we derived a tensor equation for the curl of a vector field. It looked like this. So it had the Levi-Civita, the permutation tensor. It had the partial derivative of the component with respect to a coordinate times the basis vector. Okay, if you use this form to derive the curl in spherical coordinates, you will get the wrong answer. What the hell? So this tensor by itself is actually a relative tensor, and it needs a weight factor to become an absolute tensor. What is a relative tensor is a video link in the description. The To answer this question is longer than this entire video. So if you're interested, please watch this, and I think you'll be satisfied. So because of that, I can now offer this without proof. The Levi-Civita tensor is actually equal to, this is the weight factor, 1 over the square root of the metric tensor, the determinant of the metric tensor times this permutation. This is called a permutation, the symbol. Okay, it's not a tensor. So G is determinant of the metric tensor. This is a permutation, the symbol, and it follows the same rules we've been using for the Levi-Civita, the tensors, right? So an odd permutation here, an odd permutation, you get a negative, and even you get a positive. If any repeat, you get a zero. It's the same rule, okay? Now we've been using this equation. It's just we didn't see it because we were working in Cartesian coordinates. So if we use the actual equation here, what is that in Cartesian coordinates? What's 1, right? The determinant of the metric tensor is 1, square root of 1 is 1. So it's been there all along. We just didn't see it. Okay, now that is not true for spherical coordinates. So the problem is, given the metric tensor components, there's only 3, everything else is 0. Derive the curl of vector A, any vector, I just picked A, in spherical coordinates using this new equation. Okay, I'll post the answer tomorrow. All right, see you later.